Hi, everyone. Thank you very much for joining us here at Sónar+D. Delighted to be here. The session right now is called Creativity in the Age of Quantum Computing. Now, don't worry if quantum computing means absolutely nothing to you at this point, because our speakers are going to do their best to demystify some of the basics of what quantum computing is before getting into how we're going to be able to use it, and particularly what it means for creativity now and in the future. I'm Victoria Turk. I'm a senior editor at Wired UK, and I'm delighted to be joined today by Artur Garcia Saez, senior researcher at Barcelona Supercomputing Center, Holly Cummings, worldwide development lead for IBM Garage, and Libby Heaney, artist, quantum physicist, and tutor at the Royal College of Art. Now, the way this session is structured, I'm going to give each of our speakers 10 minutes to do a kind of mini presentation that they've prepared for you to explain a bit about their work and their response to this title of Creativity in the Age of Quantum Computing. I'll then start a question and answer session with the panel, and we'll be open for questions from the floor. So please do be enthusiastic. If you've got a question, don't be afraid to stick up your hand. Don't worry if you're unsure about what something means, do ask, because this is designed for you guys to take away as much as you can. So we want to make sure that we're answering all of your questions today. To start us off then, I'd like to hand over to Artur Garcia Saez, senior researcher at Barcelona Supercomputing Center. Take it away, Artur.
So I have some, can you hear me? Yes? Okay, I have some slides. It should appear somewhere. Okay, here they are.
There we go.
Okay, I'm going to the beginning. I'm going to talk about computing from the point of view of a physicist. And sometimes we miss this point because by building computers, we've done this great job of isolating what it means computing from everything else, from what happens inside these magical boxes that we use all day long. But from a fundamental point of view, and by fundamental I mean mathematical formulation of computing, all these devices that you see on the screen are equivalent. Okay? No matter how they are built, or if they are like supercomputers or like digital watch, the inner working of these devices is the same, is equivalent. And this is a fundamental thing that we have to recover before getting into quantum computing in order to understand what it means. Okay? So what I'm picturing here is just like very old computers and the modern supercomputers. What do I mean by they are essentially the same device? The thing is that this is a very long story. For many years, we're building computers since like probably the late 19th century, and we always try to make them more powerful. And the strategies we were using were like using new technologies. Like we start with these vacuum tubes, and then we use like semiconductors, and then we put many semiconductors in the same chip, and then we build better chips, and then we put multi-core processors, and then we put many of these computers together in a supercomputer, and that makes them more powerful. And we can also improve the algorithmic part. So we have to understand that machines run algorithms, and the algorithm is the fundamental part to define the computing power of any of these devices. Okay? So we measure how good our computers are by the performance of given algorithms. So there is a lot of research done in algorithms, which is probably more important than the hardware. Okay? And all of these devices follow physical laws. Actually, a computer is like a mechanical thing. And it follows some laws of mechanics, some physical laws. Basically, they follow electricity, electromagnetism. Okay? So we are actually using very old physical laws to describe or to build computers, or to build the components of all the computers that we're using today. And actually, by restricting ourselves to these physical laws, what we found is that some problems are hard. And I think you are going to get into this, Holly, you are going to get into the hard thing later. What do I mean by hard? Really fast. That the amount of resources that I need to solve a problem is exponentially large. Okay? These resources may be memory, time, or energy, the energy that I need to run one of these computers. And it could be even worse. There are problems that we'll never be able to solve with our model of computing that we are using now, which is called the Turing machine. Okay? So there are problems that we will never be able to solve. Some other problems are really hard. That may mean from a fundamental point of view that there may be, like, for instance, mathematical theorems that we will never be able to prove. And I found that terrifying. But actually, there are good news, there are new physical theories, and actually not that new because they were formulated on the early 20th century. And the main one is quantum mechanics, which is the one why we are here. And really fast, quantum mechanics is the theory that we use to describe the systems that have very low energy, that are composed by a small number of particles, and that are sitting at very low temperature, like close to the absolute zero. So can we take advantage of using novel physical theories to build a computing device that will be more powerful than the ones that we're using? Okay? For that, I come back to this idea of there are problems which are fundamentally easy and others that are fundamentally hard. And we label these problems according to what we can do with our computers and our algorithms. Nothing prevents some new algorithm to appear that turns a problem that we think is hard into an easy problem because this algorithm is much better. But actually, we've been trying to do that for many years, and there are problems that are still hard, no matter how hard we try to solve them. And what I mean by hard is that they require a large amount of resources. And the interesting point here is probably the main takeaway from my slides, is that there are problems which are hard for a classical computer. But if we use a quantum computer with a quantum algorithm, these problems, actually there is a single problem, but the existence of this problem is fundamental, I would say. Then these problems turn easy into a quantum computer. That means that maybe you need an exponentially large amount of resources. You need a computing time of the age of the universe to solve one of these problems in a normal computer or a classical computer. But instead, by using a quantum computer, you can solve this problem in principle, in theory, because we haven't built such a powerful quantum computer yet. But this problem could be solved in minutes or seconds in a quantum computer. But there is also another thing, which is there are problems which are hard for a classical computer and are still hard for a quantum computer. And that leads me to my last slide, which is we are using quantum mechanics in order to improve our computation power, and we are assuming that we are having this quantum theory that may be not the final theory that we have to describe nature. There may be theories beyond quantum mechanics. But assuming that quantum mechanics is a final theory and we have all that there is, and using the powerful quantum computers, we will not be able to solve these problems, which are hard for quantum computers. There may be problems that are intrinsically hard, and we will never be able to solve them even using quantum computing devices, or assuming that there will not be any beyond theory or any theory beyond quantum. These problems will remain unsolved forever. And that's it. Thank you.
So quantum computing, although very exciting, it's not a silver bullet. It's not going to solve all of our problems. Thank you very much, Artur. To tell us a bit more about quantum computing, how it works, and some of those problems that it may or may not be able to help with, I'd love to hand over to Holly Cummings, Worldwide Development Lead for IBM Garage. Thank you, Holly.
Thank you. So now's the moment of truth. Yay! Right. So this is sort of the easy question. How do quantum computers work? They rely on a couple of principles which are fairly easy, except for the fact that they're so different from what we experience in everyday life. It's hard to get our head around them. And the first of these is superposition. Superposition is a fancy word which means being two opposite things at the same time. Normally that's not possible. Nothing that we interact with in our everyday life is two opposite things at the same time. But very small things often are two opposite things at the same time. They're in two different states. And the reason we never see them being in two different states is that as soon as we interact with them, as soon as we try and take a measurement, it does something called a collapse. And then it pretends it was never in two states, and we just see the single state. And the reason that this collapse is why we only realized things were in two different states at the same time relatively recently, within the past 100 years, because everything that we interact with seems to be in one state. The next phenomenon is called entanglement. And entanglement is what happens if you have superposition and you also have correlations. So let's say I have two particles, perhaps photons, and they're each in a superposed state. So they're both, say, up and down. if I take a measurement on 1, it was up and down before I do the measurement. I do the measurement, it collapses. And so I get just a single value, but I don't know which value it was. I don't know whether it was up or down, 0 or 1. So I take my measurement, I get a random value. But I know that there's a correlation between these two particles. So if one is down, then the other one is down. If one is pointing up, the other one is pointing up. So the first one I measure, I get a random result. Then I measure the second one, and I get something that I could predict. With 100% accuracy, I can say it's going to be the same as the first one. So what if I do it in the other order? What if I measure the one on the top first? I get a random result. Then I measure the one at the bottom, and I know what the answer is going to be. So this is pretty weird. And the more you think about it, the weirder it gets. Because it seems like one particle knows that I measured the other one and then changes its state. But how can it know that I measured the other one? Because they're not communicating. And we can do these kinds of experiments over huge distances, and we can see the same thing. They'd have to communicate faster than light for there to be any kind of communication between the particles. We know there's no communication, and yet we know that they know what they're doing, which is really weird, which is, I think, why we need artists to help us understand it. So what happens if we take these principles and we try and do something useful with them? So I'm just going to repeat them using exact words. So the first is that a physical state that is in a definite state can still behave randomly. And the second is that two systems, they're too far apart to influence each other, can still behave in ways that, although individually random, are still strongly correlated. And so quantum computing is taking these two ideas that make no sense but are provably true and using them for a new model of computation. And the reason they make a new model of computation possible has to do with the science that we call quantum information. So with normal classical computers, everything is about the zeros and the ones. We store information as a string of zeros and ones. When we want to do something to that information, we just change the zeros to ones and the ones to zeros, and eventually it ends up giving us cat pictures on the internet. So I can reduce that just down to two things, a zeros and a ones. And that seems really like the most fundamental thing I could do. But physics tells us it's actually not the most fundamental thing. So if I take those classical bits, the zeros and the ones, and let's say I want to represent them as arrows, just for fun. So I'd say a 0 might be an up arrow, a 1 might be a down arrow. That's my classical computation. In the quantum world, I could have a superposition of 0 and 1. So I could have something that has a bit of up arrow and a bit of down arrow. What does that even look like? Well, it turns out we can visualize it really well as a point on a sphere. So I've got an arrow, and it's pointing somewhere on the sphere. And we call that a quantum bit, and we shorten it to a qubit. And you can see just intuitively, looking at that, there's a lot more information in there than there was just in a plain old up arrow or a plain old down arrow. I've got the whole surface of the sphere to play with in terms of how I encode information, even though I only have a single bit. So what about entanglement? What if I have more than one qubit? Well, this gets really hard to draw. Nobody's come up with a perfect visualization for this, but what I like to think of it as is sort of an extra tie between these two arrows. I have these two arrows, but I can't separate them. There's something that connects the one to the two, and so as I do computations, this sort of extra thing is connecting them, and it gives me, again, an extra piece of computational power and an extra piece of information because I can play with that correlation between them. I can turn it off, I can turn it on, I can transfer it around, and that means I can do computations that I just couldn't do on a classical computer. So the cool thing about this is that 20 years ago, this was really interesting, but it was totally theoretical. But now, we're building quantum computers. Artur's job is to build quantum computers. And they're real, And the cool thing as well is that you can go play with them. So IBM was the first to make quantum computers available on the cloud. You can go play with a quantum computer on the cloud for free. So if you Google IBM Q, it will take you to a page, and it's got a bunch of tutorials. It's got programming environments, and you can actually see how it feels to program a quantum computer. And I'm going to show a couple of little demos. But before I do, I want to go into a bit of, well, what kind of problems do we think these computers can solve? We know they can't solve everything, but there are some problems that they can solve. One of the problems that shouldn't be hard and actually is super hard is the problem of trying to figure out logistics. So say I have a plane and I want to go to Barcelona and to London and to Milan and to Copenhagen. Well, what's the sensible order to do it in? It's pretty easy to work out, but despite that, we actually can't solve this problem. I can solve it for 4 cities. I can figure out the most efficient route. But when we get the number of cities up and up, it gets really hard really quick. So even though we know the formula, the calculation just takes too long. So for example, if I had 10 cities, working out the most efficient route might take 25 minutes. If it's going to save a whole bunch of fuel, that's a calculation which is totally worth doing. But what if I have 16 cities? That's not very much more cities than 10. But in order to calculate that, it would take me 27 years. So if I was a company trying to figure out my logistics, and it takes me 27 years to do my routing, by that time, everybody in the company who wanted to know the answer to that calculation has either retired, the delivery drivers have all maybe died, and my planes have been replaced by flying saucers. So effectively, I can't calculate that answer. And there's all sorts of these in all sorts of problems like this. So taking another example, caffeine is a pretty simple molecule. But because everything in it interacts with everything else, it's really hard to do calculations about. So if I wanted to model caffeine, if I wanted to simulate caffeine to really properly understand it, I'd need 10 to the 48 bits. So written out as a number, that's basically a lot of bits. And if I wanted to do this, say I said I'm going to do a grand project, and I'm going to do a full simulation of caffeine, and I did the most efficient computer I possibly could. So I said 1 atom is 1 bit. In order to get that many bits, I'd need about 10% of the Earth just to do a simulation of caffeine. And the most interesting thing about this is it's actually a really boring problem. Caffeine's pretty small. It doesn't seem like a hard problem, and yet I can't solve it. And there's a whole bunch of other problems that are hard. So for example, if I have a needle, and I bury it in a haystack, well, finding it's going to be hard. That's not a problem that we come across very often, but we come across similar problems. So for example, if I have someone's phone number, and I want to find their name, and all I have is a phone book, I have to look through every single entry in the phone book to find them, which is really boring and really annoying. But it turns out that a quantum computer can solve that problem really quickly. As long as it's easy to verify the correctness, you can use a quantum computer to search through a huge problem space to find the one right answer, which is useful. So to take an example of how this might be useful, if I'm going to do a card trick, and I have a queen, and I bury it somewhere in a deck of cards, and then I ask you, find the queen. Well, I know where it is, you don't know where it is. You pretty much have to flip each card. And we can do this on a quantum computer, but we can do it way more easily. So this is, if you Google quantum card test, you can go play with this. I've got 4 cards, so I drag the queen, I flip the cards all over, and then it uses a quantum computer to search for them, and it uses a classical computer. The classical computer took 4 tries. It had to flip every single card. The quantum computer only took 1 try, and that's running on a real quantum computer. And so if I do it again, I move the queen to a different place, I run it. Well, then the classical computer this time took 2 cards. It got a bit luckier in the order it did them. And the quantum computer still took only 1 attempt. So that's a useful speed up. That's just a game, but you can do this for all sorts of other problems as well. So that is a game, but we do see this being useful in real problems that affect industry, that affect business, that cost a lot of money, or that have big health implications. One of the things that quantum is really great at is simulating chemical molecules. That was the problem that first led to the discovery of quantum information. And so if I can simulate chemicals, then I can do materials design. I can find new battery technology. I can find new drug technology, potentially life-saving drugs. Quantum computing also turns out to be really good for artificial intelligence, things like classification problems, machine learning. It's also really good for a whole bunch of financial problems, because financial problems often involve some level of optimization. Quantum computers are great for optimization, so you can do portfolio optimization, you can optimize your arbitrage, you can do risk optimization. And finally, as I spoke about, potentially very interesting for logistics as well. So that still leaves the question of what does it all mean? And so with that, I will hand over to Libby for the really hard stuff.
Can you hear me now? Yeah, great. Okay, it's really super exciting to be here. For those of you that don't know my background, I spent around 8 years working in quantum computing, like with people like Artur, not in universities, not at IBM though. And then around 6 years ago, I retrained as an artist in London. And part of my job at the Royal College of Art is to think about the intersection of quantum computing and art. So I'm going to throw out some questions to you all. As Holly said, what does it all mean? And bear with me, because these are quite speculative questions that draw on some of the science that we've heard from these two previous speakers. So one of the things that I could sit here and talk about, we've heard about problems such as machine learning and how quantum computers are really good at solving linear algebra, which is also used for ray tracing with virtual reality, and talk about how we could be building new, sort of more powerful, developing more powerful tools that already exist. So how can we make really powerful virtual reality? How can we make really powerful machine learning? But as an artist, I do want to ask what it means and think a little bit more about the sort of social, political questions that artists can ask that quite often get lost in science, because we're allowed to speculate, we're able to get things a bit wrong and to create meanings that maybe don't quite make sense right now, but in the future maybe they will make more sense. And also towards the end of what I'm saying, I'll talk a little bit about art made by a quantum computer, think a little bit about quantum images. Okay. So I said, what does it really mean for artists to think speculatively about quantum computing? How will quantum computers impact on society or politics in the future? And this is something artists do very frequently. If you look at some of the works around here, or hear Memo Acton talk about his work here, just across the way there, we're always questioning what the technology means within a context, and often in a critical way as well. So one of my artworks that I made 2 years ago, called Quantum Breathing, speculated about a new future technology. And we've already heard from Holly how quantum computers are really good at searching large data sets. And they can find much more quickly data compared to how a digital computer can. So what I did as an art project, I speculated around a new technology called quantum virtual reality, where quantum computing interacted directly with the brain via a brain-computer interface. It's kind of like what Elon Musk is going on about most of the time at the moment. So the artwork was an installation centered around this virtual reality, which was a fictional prototype. It wasn't real. There was no quantum computing in it. But what the artwork posed was questions about if we had such a technology, and this technology could search inside our brain, perhaps in our subconscious, and produce visuals that were really seductive, visuals that we really, really wanted to see. I don't know, maybe porn, or maybe something else, who knows? But then, as an exchange to get this really amazing new visuals, these corporations, this quantum virtual reality corporation would extract, using the search algorithm, would extract private data from our brain. So really what I was proposing in part with this artwork was a new quantum surveillance regime, because obviously with all the digital technologies we have at the moment, we're giving our data away to Facebook, Google, every moment of the day. So that's a very specific example, but we can also think more widely. Currently, we live in a world where the Western worldview is dominated by information and information technology. We see the world as data that can be sensed through technologies like this, but also through tracking, Fitbits, lots of different technologies. And this data, maybe from Tinder, Love, whatever, we can sense it, we can collect it, and we can model the world. And this is a very computational information view of the world that we have. And this sort of seeing the world through new dominant technologies is not new. When the steam engine was first invented, there was a worldview where everything, including the body, was a machine. We were cogs and pulleys. And this was reflected through art, like in Marcel Duchamp's Nude Descending the Stairs, where the body, the privileged human subject, is a machine. And that, the artwork was kind of rejected at the time, because it was quite controversial. So one of the questions we can ask as artists and other creatives, writers, whoever, and scientists as well, is when quantum technologies are fully developed and they go beyond this embryonic prototype stage that we currently have with the one on the cloud here, which is fantastic, but it's still very small, how will that change the way humans see the world and ourselves in it? What is this quantum view of the world? And I think already it's there in philosophy and art history a little bit, but when quantum technologies are really out there, what will this look like? I brought a quote with me that I really like from a feminist writer called Sadie Plant, where she thinks about the history of women and technology. It's from a book called Zeros and Ones, and she starts off with this poetic piece of writing that sort of thinks about what a quantum world might mean, and this is just to provoke some ideas in you, so I'll just read this short quote to you. I love this. So those were the days when we were all at sea. It seems like yesterday to me. Species, sex, race, class. In those days, none of this meant anything at all. No parents, no children, just ourselves. Strings of inseparable sisters, warm and wet, indistinguishable one from the other, gloriously indiscriminate, promiscuous and fused. No generations, no future, no past, an endless geographic plane of micro-meshing quanta, pulsing, limitless webs of interacting blendings, leakings, mergings, weaving through ourselves, running rings around each other, heedless, needless, aimless, careless, thoughtless, amok. Now, obviously, this is a piece of poetry, but for me, it really reminds me of the sensation I have when I'm working on quantum physics with concepts like entanglement and superposition. But what Plant also proposes here is this sort of fluidity where binaries, that like race and class, that can often cause prejudices, are deconstructed. And I think perhaps a quantum worldview will allow sort of these categories to be deconstructed or played with more fluidly, perhaps. So just to change slightly, I'll now just finish by talking a little bit about art, future art made by full-scale quantum computers. So we've heard from the earlier speakers that we do not know. So the quantum computer can compute problems that have never been solved previously. We've heard from Holly about the distance problem or finding needles in haystacks. So when we start computing data with quantum computers in the future, what new visual patterns or sonic patterns will they produce? And as humans, how will we even understand what they produce and what meanings? Like, how do we attribute meanings to these things? Can we even do this? I'm sure we'll find a way, but it's interesting to think about these new sort of, it's particularly with quantum machine learning, I think this could be quite quite interesting. If we think of digital images currently, so digital images have really changed the world. We're all creators of digital images, sharing them on the phone, sharing them across Instagram, and so on. So we understand the world differently because of these images. We have instant access to news and to different things that are going on, whether good or bad, across the globe. Also, with the rise of artificial intelligence and deep learning, we can now create fake videos of Mark Zuckerberg or Barack Obama saying things that they've never, ever said. So digital images have really changed how we see the world. So another question we can pose is, how will quantum images, what impact will they have on the world? And of course, it's difficult to predict at the moment. But one of the things that we haven't heard yet from the speakers is that it's impossible to copy unknown quantum information. So if you have information stored on a quantum computer using entanglement and superposition, if anyone has this data on the quantum computer, but they don't know what it is, it's impossible to copy it and share it. So that really changes kind of our ideas around images. If we have images stored on a quantum computer, we might not suddenly be able to share them and send them as we would have previously, because the recipient needs to have that precise information about what that image was before they open it. It's not like an attachment in an email where you can just look at it no matter what it is, even if people haven't said it previously. So I think one of the questions that Art can really get at with these new technologies is who will own these future technologies, and also, what will happen in terms of the surveillance and what we see with them as well. I think artistic research alongside the scientific research is really important at this stage of quantum computing's development. Start generating language around these new technologies before they become really developed. Yeah, that's it. Thanks.
Thank you very much, Libby. Thanks for giving us so much to think about as well. Lots of food for thought there, for sure. Yeah. Now we're going to get into the panel discussion and question session. So if you are thinking about questions, I will get to audience questions soon, so do start thinking about those in your head. First of all, I'd like to start off just by kind of bringing us back to the present day a bit. So where exactly are we with quantum computers? What stage are we at? There's a lot of hype. Quantum computers do exist, but where are we at? Artur and Holly, perhaps you're best placed to answer that one.
Yeah, I can talk about that. We like to divide it into 3 stages. One is quantum foundations. So that was where we were up until a few years ago. Quantum information theory was being developed, but it was something that was only in the labs. We didn't even know if it would be useful. Where we want to get to is a stage we call quantum advantage. And that's where we can use quantum computers to solve problems that we could not solve with a classical computer, and actually, get the answer and do things that we couldn't do before. We're in an intermediate stage now, which we call quantum ready. So that means that it is going from the labs into industry. Companies are playing with it. We're so close to having it do something useful, and we want to be ready, but we're not quite there. So then the next question is, well, how long will it take to go from ready to advantage? That's hard to say. It seems like 2 to 5 years is probably a good sort of number, and in that time we'll be able to solve problems. But there's an important qualification there, which is that we'll be able to solve some problems. The quantum computers that we'll have in 5 years will be what we call approximate quantum computers. So that means it will give an answer, but there's probably some noise and errors in the answer. So if you're trying to do something where an answer that's close is good enough, that's great. If you're trying to do something where the answer needs to be perfect in every single bit, then that's going to be a ways further off, probably 15 to 20 years, if we even get there, because there's huge technological leaps that we need to take between where we are now and there.
And Artur, as a researcher at the Supercomputing Center, you're already working with this kind of technology. Will this always be restricted to the realm of researchers and people like yourself working in those centers? Or, who will have access to this technology? Is it something that people in the audience today might one day be using?
Well, I would say that that already changed when many companies start doing research. So quantum computation was like a field of research only in universities. And when this technology becomes somehow mature with like this 5 years scenario of having applications for industry, then companies like IBM or others are investing and doing research by their own. So that completely changed the way we researchers related to our own field, because the way we develop, I mean, this is a technological development that needs money. And the way we get money in public institutions is totally different as the way the companies work. So I would say that changed a lot. The idea of having a quantum computer in the pocket, which is probably one of the ideas that everybody may be thinking of, like, oh, in 10 years I will have my quantum phone. And I mean, the problem is you have to control a quantum system, and that means, especially in this technology as we are using, or IBM, which is like these superconducting qubits, you need very low temperatures. That means like a super expensive fridge that probably is better to have only a few in the world and you access remotely from the cloud. That's probably, but as we are doing with many other things, like office suites or things like this that you use remotely now.
So you think the hardware will probably just be in a few places where you've got those really big fridges, but people may be able to interact with that via the cloud. Great. And Libby, obviously, you're in a very interesting position as someone with a background in quantum physics and also art. Lots of people at Sonar, I imagine, are more on the artistic side rather than necessarily being quantum physicists. Do you think that artists who don't have that background can interact with this sort of technology? How do they get into it? How can they have their say?
So, yeah, it's a really important question, and one that I'm still grappling with, because obviously it can be a difficult subject to get in with. There's lots of artists previously to myself who have written really eloquently about quantum. James Elkins is an art critic, the artist Roy Ascott, and others who I can't remember right now. And so you can start using these other people that are used to playing between the two different disciplines, and myself and others that write, and you can use metaphor and analogy to start getting into it. So when I teach this to my MA students at the Royal College of Art, every year is different based on the previous year, but one of the things that I use quite often might seem quite, I don't know, like flippant, but Alice in Wonderland, the story, is actually a really good starting point to start talking about some of the counterintuitive ideas behind quantum computing. There's also visual illusions. You know, these illusions where you see a vase or two people's faces, and depending on how you look at the system, you see the vase or two faces. So your perception is changing what you see, but really both exist at the same time. Now, qubit, a superposition, is way more complicated than that. But these approximate images, because we can never really represent quantum physics, it's too complex. That's why it's so good at problem solving these difficult problems. We saw in Holly's talk that we couldn't represent entanglement. But these approximate images kind of circle the void around what quantum is. And there's lots of information out there about this. Just one other point is scientists generally, in my experience, are very happy to collaborate. People, at least in the UK, tend to have money for outreach, and they want to work with artists to communicate their work. So, yeah, drop them a line if you're into that type of thing, and see what they're up to.
Fantastic. Have we got any questions from the audience? Is anyone brave enough to go first?
One down here.
Oh, one right at the front down here.
Hello, thank you for the talks. Are there common tools, or programming language for computing, quantum computing? Like, I know there is IBM quantum computing cloud, right? And there is Microsoft. What would you recommend to wait until it will be unified to some one tool language like C++, but for quantum computing? Or just play with any of these without any difference?
I'd recommend getting stuck in now, because I'm not sure it will ever be unified. We certainly don't see a unified language for classical computing. There's a whole bunch, and they're good for different kinds of problems. And I think that's probably what we'll see with quantum computing as well, that there's, for various reasons, I think there's always going to be multiple. So choose the one that works for you, choose the one that makes most sense to you.
Artur and Libby, have you got any recommendations of tools or resources that people might want to check out if they want to learn more?
I would say it's a moment where it's very difficult to decide what do we need as a field. Like, do we need a unique language for everybody to use? And all these proposals that there are now are allow you to have a clear insight what's happening beneath, like on the real device. You may control many parameters. So I would play around with as many as, that's what I do normally. I try to build some tools in order to like reuse parts of code, but mostly I use different libraries. So and I would say the learning curve is not that steep, so it's a good exercise.
I mean, for me, I've used, like when I left quantum physics, I was still calculating pen and paper to think about quantum computing. And now, obviously, it's developed so much further. So when I've revisited through an artistic lens now, I've used IBM's Qiskit. There's this researcher at IBM called James Wooten, who does lots about kind of developing images with quantum computing and games with like the quantum computers. So I know him from previously, but so we have this dialogue going on. But I think I found IBM quite good to get back into it. Yeah, just bigging you up there, Holly.
Any other questions from the audience? Yes.
Check. Okay, so can you discuss a little bit about quantum computing as it relates to encryption and blockchain technology?
So that's quantum computing and how it relates to encryption and blockchain technology. I think, Libby, you touched on the idea of encryption a little bit in terms of
I could try and have a go at doing it, but if anyone else wants to go for it, like, you can go, yeah.
So besides this quantum information field, there has been this ongoing research for many years on quantum information, or quantum cryptography. So the promise of quantum computers is that they may be, the problem that they are very strong to solve is factoring. So you may break RSI keys easily, okay? So that may kill encryption as we know it today. But we have quantum cryptography. And it takes the idea that she was commenting before, that you cannot copy information when it's written in a quantum state. So we have a very powerful theory of quantum cryptography that will allow to have secure, unconditionally secure cryptography, even with more advantages than we can imagine with classical crypto. For instance, you would be able to detect if an eavesdropper is getting your messages. That cannot happen with normal cryptography. So even if they are encrypted. So there is like a big solution for a big problem that we are creating on the same field. So I think that's more or less.
Yeah, I mean, I can jump. I've looked a little bit into the relationship of quantum computers and the blockchain. I think it's interesting. I don't know the science as deeply as maybe Artur would, so from my understanding is quantum computers will be able to decrypt, decode the blockchain. So blockchain is not safe to quantum computers. People have proposed, theoretically, quantum blockchain that uses quantum concepts, quantum properties like entanglement, superposition, to make it safe again. But there's also another field called post-quantum classical cryptography. So you're still working with classical computers, but you're trying to build algorithms that are resistant or cannot be sort of attacked by quantum algorithms. And but then it's not always so certain if there's not another quantum algorithm that hasn't been discovered yet that can then break these. So there's like a bit of tension in the field, I think. That's my understanding, but yeah.
And I guess that's maybe an important distinction just to underline, is that quantum computing is not just the next version of classical computing. It's not just, a more effective supercomputer, right? The way it solves problems is completely different. And so, I think that's important to understand for anyone who's maybe not been particularly introduced to quantum computing, although it could solve some problems and although it could, for example, break classical encryption, other problems that classical computers find easy, quantum computers may be absolutely useless at, right? Yeah.
I would say that for a while they will coexist, that we will create this hybrid technology where we will have different kinds of computers and each one will be used for a different task. They will specialize. It's pretty similar to what happens today with graphical processors that are used for machine learning. I mean, this is a field that got boosted by a new technology that was sitting around using for games, but once applied to the right field, it boosted it. So with quantum may happen something similar.
Yeah. Any further questions from the audience? Do put your hand up if you've got one. We've got mics roving around. I'm happy to continue discussing with our panel if not, but the more you put your hands up, the less you have to hear from me. So yeah, I wanted to get into some of those applications and some of those problems that quantum is of great hope for, really. What to you, Holly, are sort of the most crucial applications that quantum could have? What are the big issues that it may be able to help us with?
One of the ones I mentioned was the battery technology. And I think that seems really relevant because of its potential impact in terms of climate change and that kind of thing. What limits a lot the application of electric to planes, for sure, and to cars to some extent is the battery technology, because batteries are a pretty inefficient way of storing energy. They're heavy, and you can't get much energy into them, even though they're very heavy. And so if we can use these sort of chemical modeling problems to search in the lab for a new battery technology, that potentially has a huge impact.
And Artur, what would you say is sort of one of the most critical applications for quantum when it gets to that stage?
Wow. That's a difficult question, because from the fundamental point of view, looking for applications of things that change dramatically some field is like I'm mostly interested in the fundamental part. But of course, optimization. I mean, solving problems that we are already solving now. That's really important, like optimization. And I mean, optimization is everywhere. So you could be using it like for every field. And the dream is to replace some of the libraries we're using with all these structure of quantum algorithms and things, but that the user doesn't care about what's going on beneath. So.
Holly, it's interesting you bring up climate change, because that's obviously an issue that's been mentioned many times already at Sónar, at the first day of the event. And one of the problems with quantum computers, which you alluded to, I think, Artur, is the problem of cooling. They need to be kept really cool, which requires a lot of energy, right? So how do we make sure that quantum computers are environmentally friendly, or at least kind of reduce the potential burden that this new technology could bring?
That's a good point. No, go.
I was just going to say, I think there's a trade-off. So I think certainly at the moment it is definitely more costly. The current technologies, they're not just cold. They're about 0.15 Kelvin cold, which is colder than the space between the stars, which is quite romantic, but quite expensive. But you can do the calculation much more quickly. So there's probably you can do the curve and you can map it and you can say, well, if I can do my calculation 100 times more quickly and the effect of my calculation is actually helping me save plane fuel, then even though, per minute the calculation was more expensive, per answer the calculation was maybe less environmentally costly.
That's a good point, because we normally compare technologies or computing technologies in terms of speed or memory or like exponentially speed up or these kind of things. But energy has to play a role in this equation. And quantum computers now are like energetically expensive, but so are supercomputers. I mean, building supercomputers means bringing a lot of computers together, and that has like a very high power expense. So it could be that what we are interested in is how these energy consumption depends on the size of the problem you are solving. So it's like a trend, and you want to compare trends. How many energy do we need to solve a problem that large as these optimizations in both systems. That would be like a fair comparison. And in that sense, I mean, while cooling down a system is expensive energetically, running the experiment it is not. So you would be like getting all these computation once you have cool it down for almost for free, which is totally different at what happens with supercomputers.
So again, I guess it's having to think in a whole different framework for quantum. It's not just kind of scaling up what we already have. On the subject of applications, Libby, you've spoken a lot about how artists can help to visualize this new technology and to play with that. How do you see creatives and artists using quantum tech in their work? And when do you think that will sort of be available?
Okay. I mean, myself and students at the Royal College of Art have already used 4-qubit quantum computers from the University of Bristol to experiment with what future art with quantum computers might look like and what they might mean. But because I think, how many qubits does IBM have? 16, is it now?
Yeah, we've got 16 and 20, and we've got a 50 that's been announced.
Yeah, so it's still very difficult to do anything that you couldn't just make up with pen and paper even, let alone After Effects. But in the future, because we've heard about how quantum computers are good at linear algebra, and linear algebra is used in graphics cards for ray tracing, for virtual reality, and also solving or developing neural networks. A neural network is essentially just a big system that is dealing with lots of linear algebra. So we can imagine artists working with virtual reality in new ways, where it's very difficult to imagine because you're trying to get beyond this kind of classical, what we're used to seeing, and into some sort of quantum environment. But essentially, you will see patterns that are generated, or perhaps generated from quantum computers. So, like wave behavior in quantum physics is very different to wave behavior how we see like water in a pond. So if we throw a stone into a pond, we see the ripples go out, and we're used to seeing this. Whereas a quantum wave looks quite different and quite uncanny. So perhaps in a future virtual reality or future quantum graphics, we might start to see some of these quantum simulated visuals that will allow us to sort of imagine the universe or imagine different worlds, parallel worlds in different ways. It's hard for us to understand that right now, and that's what I was trying to get at in my talk. Also, artists working with machine learning, that will change as well. Yeah. So
I think that there is one thing that artists we may think that as a scientist we need some feedback from artists in order to understand what we're doing. I mean, we may reach this point when we go to a bigger number of qubits where understanding what's happening there, it's beyond our capabilities. So we need new inputs. It may come from artists or from a different field like math or computer science or I don't know, biology, whoever. But we may need this different view to help our research because we are always at this risk of doing something that we don't really understand.
Yeah, my experience when I've collaborated with quantum physicists working with quantum technologies is that if the collaboration is long enough, so the artists that don't have a background in quantum physics gets used to thinking in a quantum computational way, then the conversations, as you say, between the scientists, engineers, and the artists are really productive in both ways. But it takes a long time, I think, like a year or 6 months of sort of back and forth as people absorb this new way of thinking and understanding computation.
Got a question from the man at the back there.
Yes, so this comes from someone who doesn't know so much about quantum physics, but what I've read is that people are still not sure if quantum physics are real or not. With these quantum computers, is it proven that actually quantum physics is like a real thing that's happening, or could it still be something that's just an anomaly or something?
So quantum physics is actually one of the most experimentally verified theories. It's absolutely real. The only problem is it's not comprehensible, and that's why people struggle with it.
I think you may be alluding as well to some early claims of people who said they had built quantum computers, and there was some kind of doubt around how the quantum computers were. I think perhaps that might be what you've come across.
I mean, as any physical theory, we don't know if that's the final theory. That's a fundamental question that people are still doing research for that. But we haven't found anything that, as she was saying, I mean, it's the most tested theory with a level of accuracy that no other theory has ever provided. So I'm pretty sure it's a good theory.
So about as certain as you can ever be about a theory.
And of course, our understanding does continue to evolve as well.
No, for sure. We've got another question at the back and then one down at the front here.
So this is just for, if you can share from IBM perspective some of the examples of your clients that quantum computing really changed the way you operate, or real impact on what they do for the people or for the clients.
Yeah, so we're not quite there yet. So we have what we call the Q network, and that's a bunch of clients that we're working with to drive the science forward. So for example, we've got, I think, Mercedes-Benz, we've got JP Morgan, we've got sort of across all industries. But with all of them, we're still in that ready stage. We're not in that advantage stage. So we're still trying to make it happen, thinking, okay, and in a few years we're going to do this, and it's going to really allow us to solve something new, but we haven't solved anything new yet.
Hi. I'm wondering if there's a relationship between quantum computing and the future AI, artificial intelligence, robots making, and how would it work in the future, to control the robots and stuff.
Great question there, the relationship between quantum computing and AI/robots.
So one of the main lines of research now is to apply all these algorithms in order to improve our techniques for machine learning. And there are some results because the operations that we use for training a neural network can be sped up potentially by a quantum computer. So that would be like a direct application. More fundamental question is if there is any quantum phenomena involved in the human brain. And that's also like it's a very speculative and things like this. But if we are thinking about models of computation, the brain has to appear somewhere. We are computing things all the time with a very efficient computer here, which we are not sure how it works. And there are speculation about there may be some quantum effects involved. So if we want to mimic how the human brain works, then we need some quantum computing. But that's super speculative. So that's,
I like it.
Any final questions? We've got just a couple minutes left, so now's your last chance if there's anyone dying to ask a question. I don't think so, so I'm going to end the session there with one last request from you all. Now, Libby, you said earlier that one of the great things about moving away from being a physicist to an artist is that you're allowed to speculate a bit more and kind of think about things that may not turn out to be exactly right, but are still helpful in helping us understand these concepts. So I'm going to ask each of you, I'm going to free you up as well, scientists, to speculate a bit about what's it going to look like when we reach that stage of quantum advantage. Describe for me, what is the quantum advantage world?
Yeah, for me, I mean, one of the things that I've spoken a bit about previously to artistic audiences is at the moment we're still trying to reach this quantum advantage. Now, quantum computers can encrypt all the RSA codes. So depending on who builds the first full-scale quantum computer has an advantage over, in principle, over a lot of different businesses and governments and so on. So I think we just need to be aware how they could be used in these nefarious ways, as well as talking about the really positive ways they might be used in the future. So
quite chilling dystopian vision from Libby. Artur.
I would say what I'd like to see is like that this technology becomes like a popular thing, to the level that kids will learn it when they're like kids. And that may bring a very funny side effect, which is the problem with quantum mechanics is that we normally learn quantum mechanics when we are like grown-ups, and we have a fully established intuition about the physical world. And if you train people from an early age to think in a different way. That may change the way they will think all their lives. So, and for that, we need this technology to become something as common as a mobile phone or a smartphone. And that may be some of the side effects of having these computers, quantum computers everywhere.
Okay, that's quite a democratic vision from Artur. Holly?
Yeah, I'm just, I really love that. Because Artur's exactly right, that quantum mechanics, it's so different from our experience of the everyday world. And as you say, we only learn it when we're a grown-up, and only a small number of us learn it. But if quantum computers become more pervasive, then that knowledge might go down. And then you're right that does have fascinating implications for how we approach other things as well. I think it's so hard to predict the changes that technology makes, though, because so many of the technologies that we use now were intended for something completely different, and their creators didn't anticipate their popularity. Even taking a really trivial example, text messaging. When text messaging came out, even the phone networks didn't really think it would be popular because people thought that people wanted to use phones to talk to each other. And it turns out that talking to each other is the last thing people want to use phones for. But it took us quite a while to realize that.
Fantastic. Well, thank you to all of our speakers. Please give a round of applause to Libby Heaney, Holly Cummings, and Artur Garcia Saez. Thank you.